Hey there, chemistry students. So we finished our first unit. Our first unit was about lab safety and lab equipment. We've talked about that. We know how to use our lab equipment. We know how to be safe in the lab now. Moving on, Unit 2 is about atoms. In Unit 2, we're going to learn about atoms. We're going to learn all about atoms. We're going to learn about the parts of atoms, how they're made up, how they're laid out, all this kind of stuff. Atoms are like the basic building block of all things in chemistry. So we're going to talk all about atoms. We're going to learn all about them. And our first target here, we're going to learn about atoms and elements here. This is our first lesson in the unit. And our target is to be able to tell the difference between an element, a compound, and a mixture. So let's go ahead and let's talk about these things and let's see what they are. So I have here some different substances, right? And the world is filled with different substances. There are millions of different substances in the world. Here I have some tap water. It's St. Anne tap water, so hopefully it's water. Here I've got, this here is sulfur. It's powdered sulfur, right? Here I've got some aluminum. That's aluminum. And then I've got some wood right here. This here is wood. So we have some different substances here. And, you know, these are just 4 different substances that I randomly collected out of my classroom. There are in the world millions of different substances that you could take a look at. It's kind of a natural question for people to ask. What makes these substances different from one another? If you think about them, they have different properties. This here is a liquid. The other 3 that I showed you were solids, right? There are other substances that are gases. This here is yellow. This here's kind of yellowish. Here's metal colored, right? Kind of silverish. So, I mean, they have different properties. Some of them will conduct electricity well. Some of them won't. Some of them will conduct heat well. Some of them won't. Some of them will be flammable. Some of them won't, right? The different things have different properties. And it's kind of a natural question for us to ask. What gives different substances their different properties? And hopefully over the course of this unit, we're going to kind of come to an understanding of what gives different things their different properties. So let's go ahead and let's take a look at some of these things. Let's talk a little bit about some history here, okay? Going back, way back into ancient days, people would naturally ask the question, what makes different substances different from each other? If you are out there in the world and you know, in ancient times and you had to take care of yourself, you had to make your own soap, you had to find your food, you had to, you know, all this stuff, you might find it useful to know how things work, right? And in ancient times, people would ask the question, what makes different substances different from each other? Maybe it can help me find something that will work better for whatever I'm trying to do, right? And one of the first people we have that wrote anything about this, you can see his picture up here. His name is Democritus. He was an ancient Greek philosopher. Democracy is named after him, right? And Democritus is really kind of the first person that we know of who wrote of an idea of things being made out of discrete units, right? Democritus' thought was that things are made out of tiny little indivisible spheres, right? Indivisible means you can't break it down into smaller parts. And so from that ancient Greek word for indivisible, we get the word atom. So Democritus is kind of credited as, you know, the first person to have this idea that atoms exist. Now, he wasn't a scientist. He didn't have any evidence. This was just, you know, his thought, his philosophy, right? But this was way back in BC, ancient Greece, right? Democritus, first person to come up with the idea of atoms. Now, an atom is a really small thing. And of course, in ancient Greece, they couldn't have had any evidence that atoms actually exist. And fast forward a couple of centuries to the 1700s, the 1800s, what we know of today is chemistry was starting to take shape. Scientists were starting to do experiments where they combined different substances and see how they reacted with each other, right? For example, you could take water and you could break it down into other substances, right? Some substances could be broken down into other substances. Some substances could be combined to form new substances. There was a guy by the name of John Dalton. John Dalton was an important English chemist, and he found that when substances break down, they always break down into the same ratio. So for example, when you break down water into hydrogen and oxygen, you always get twice as much hydrogen as oxygen. And he also found that the reverse was true, that when you combine substances, they always combine in the same ratio. And this he called the law of definite proportions. The law of definite proportions stated that substances always either combine or break down in the same ratio, right? Dalton tried to explain what he had observed by using this ancient Greek idea of atoms, right? He figured that there must be different kinds of atoms that made substances different from each other, right? And he also figured that the different kinds of atoms could join together to make more complex things. So for example, water would be made out of two different kinds of atoms, a hydrogen atom and an oxygen atom. And since they always combined in the same ratio, there must be 2 times as many hydrogen atoms in it as oxygen atoms. That takes us to this idea of there being different kinds of atoms, right? And today we know about 118 different kinds of atoms, and you can find them all listed in this table. This table is called the periodic table, right? And each substance that's made out of only one kind of atom is called an element. And so if we're talking about, say, a bar of iron that's made out of iron atoms, that's an element because it's made out of just one type of atom. If we're talking about that sulfur that I have that's made out of sulfur atoms, that's an element because it's only made out of one kind of atom. If we're talking about the water that was in that beaker, which is made out of hydrogen and oxygen atoms, that's not an element. You won't find water up here because it's made out of more than one kind of atom, right? These are all the different kinds of atoms that we know about. Water isn't up here, it's made out of more than one kind. Water is made out of oxygen and hydrogen, out of more than one kind of atom, right? But the other ones that I mentioned, iron, it's right there, sulfur, it's right there. These are different kinds of atoms, and a substance that's made up of just one kind of atom we call an element. Okay, well, we know about 118 different kinds of atoms. Only about 92 of them occur in nature. Up to number 92 here, those ones occur in nature. All the ones that are bigger than that have been made in a lab, synthetically. They're not natural. They don't occur naturally. You're not going to go out in nature and find cobernicium, right? It doesn't exist in nature. It's been made in a lab. When we look at these elements, each element has a symbol that's used to stand for it, right? So some of them are obvious, like take for example, carbon, right? Carbon's symbol is a C. It's just a capital C, right? Some of them are just one letter like that. Some of them are more than one letter. Like let's say we're talking about iron. Iron's symbol is Fe. A little bit different, right? Some of them are 2 letters. If they're 2 letters, the first letter is a capital letter. The second letter is a lowercase letter. So whether it's 1 letter or 2 letters, that first letter is always a capital letter. And if there's a second letter, it's a lowercase. Don't put capital F, capital E, that's not correct. Okay, some of the symbols are obvious, right? C for carbon, S for sulfur, O for oxygen, but some of them are less obvious, like Fe for iron. Why is it Fe for iron? What you got to keep in mind is everybody in the world uses the same symbols, regardless of what language you speak. So some of the symbols come from English, C for carbon, right? Some of them come from other languages. Particularly, a lot of them come from Latin. The Latin word for iron is ferrum. Now you can see where the Fe comes from, right? One interesting one, tungsten. The symbol for tungsten is a capital W. Why W? Well, it comes from the German word for tungsten, Wolfram. W, right? So, W for tungsten because it comes from German. But, some of them, Cu for copper, comes from Latin, right? A lot of them come from Latin, which is why they have symbols that you might not expect. Some substances are made from different kinds of atoms that are joined together. A great example is water. Water is made out of two different kinds of atoms joined together, hydrogen atoms and oxygen atoms. You can see here a water molecule, right, made up of two hydrogen atoms and an oxygen. When we have more than one kind of element chemically joined together like this, we call this a compound. Water is a great example of a compound. Many other things are examples of compounds. Salt. The salt that you put on your food is made out of sodium and chlorine atoms. It's a compound. Ammonia in your glass cleaner is made out of hydrogen and nitrogen atoms joined together. It's a compound. A compound, different kinds of atoms joined together chemically. Compounds don't have a symbol the same way that elements do, right? We know about 118 different elements, and we can give them each their own symbol because there's only 118. Compounds, there are millions of known compounds. There might be tens of millions of known compounds. They don't have their own symbols, but they do have a way to make a symbol for them. And the way that we make a symbol for a compound, we call it a formula, right? A chemical formula. And what we do is we put together the elements that make up that compound in their proper ratio. So, for example, you can see the formula for water here, H2O. You can see it's made out of hydrogen. You see the symbol for hydrogen, H, and oxygen. You can see the symbol for oxygen, O. And there's a little 2 in there that tells you that the ratio of the hydrogen is 2. And with no little number next to the O, we know that it's 1. If there's no number next to it, it's implied that it's 1. That happens a lot in chemistry. If you don't see a number, it's 1, just like in algebra, right? So we can look at the formula and tell there's hydrogen and oxygen atoms, and they are in a 2-to-1 ratio in this particular compound. So for any compound, we can put together a formula that tells us which elements that make it up and what ratio they're present in. The other type of substance is what's called a mixture. So we've talked about the elements, we've talked about the compounds, and then the third type is what's called a mixture. A mixture is when you have different substances. They might be elements, they might be compounds, but they're mixed together, but they're not chemically joined together. Right? Remember, in a compound, you have different elements that are chemically joined together. In a mixture, you have things that are not chemically joined together. Air is a great example of a mixture. Air is made out of mostly nitrogen, and then there's some oxygen, and then there's some other stuff. But these different things are not joined together chemically. This is a mixture. So really, what's the difference between an element, a compound, and a mixture? Pretty simple. Think about Legos. If we've got Legos that are all the same kind of Lego, that's an element, right? You can see the picture. There's more than one Lego. They're stuck together, but there's only one kind. That's an element. If we have more than one kind of Legos, and they're stuck together, look at the picture, more than one kind, and they're stuck together, that's a compound. And then, if we have some Legos, more than one kind, different kinds, could be stuck together or not, just all mixed together, that's a mixture. Alright, so there was a little bit about atoms and elements. Hopefully that helps us to be able to tell the difference between elements, compounds, and mixtures. Going forward in the next lesson, we'll learn about some different parts of atoms and how they're organized. So until next time, take it easy.